What's up, team? Today we're talking about functions. We're doing an introduction to functions. You see the learning target right above. It says, I can represent relations and functions using tables, mapping diagrams, and graphs. And then there's a reminder that talks about functions specifically. We'll talk about that in a bit. Okay, the easiest way to describe functions, at least I believe that the easiest way to describe and think about functions is thinking about vending machines. So check this out. I got a vending machine here for you, and this is a Pepsi vending machine, a couple different varieties. You've all seen them before. You know how they work. You put the money in, you press the button, the drink pops out, right? Well, let's think about these in terms of functions. So when you put the money in and you make your selection, so you look at this machine, it looks like there's Pepsi and Diet Pepsi, water, looks like Mountain Dew, a few different varieties of Gatorades, and then, I don't know, those Sobe, like Life Waters or something. I'm not exactly sure what some of those on the right-hand side are. Regardless, say I go and I want to get the purple Gatorade. That's what I'm seeing. That's what I want from this machine. If I press that button for the purple Gatorade, and I'm expecting to get the purple Gatorade. That better be what comes out, right? So if I press the button, purple Gatorade comes out, takes my money, whatever, like the way it's supposed to work. I get my Gatorade, I'm happy. We would say that that machine is functional. It works. It's working appropriately. The expectation was when I press the button for the purple Gatorade comes out. So in math terms, we would say that the input to this function is me pressing the button with the purple Gatorade. And the output is the machine actually giving me the purple Gatorade, the bottled beverage. So this is a functional function, or it's a function that's true, that works. Now let's say I went and I pressed that purple Gatorade button, but Mountain Dew popped out. Well, I still got something. I guess I got my money's worth, but it's not what I wanted. So we would say that that would not be a function. So a function is a relation where every input has exactly one possible output. Meaning every time I press the purple Gatorade button, purple Gatorade is what comes out, unless it's sold out, of course. And same thing with the Pepsi. If I press the Pepsi button, I'm getting Pepsi. If I press the Mountain Dew button, I'm getting Mountain Dew. Now, once upon a time, when I was a little Josh, there was a vending machine at a grocery store next to this card shop. The card shop is where I'd go play Pokemon cards with my friends on Saturday mornings, and their grocery store right next to it is a Winco. And they had a vending machine, the Shasta vending machine. And for one of the pops, if you press the button for black cherry pop, you pay the quarter. At the time it was a quarter. Pay the quarter, you press the button, you get a black cherry, like a can of pop, like the 12-ounce cans. Awesome, right? That's how vending machines work. But this particular machine, somebody found out every other time you made a purchase, it would give you two of them. And so I had two friends, the three of us would go every Saturday. For 50 cents, all three of us can get a pop, because no matter what, the first time we put the money in, we get one. Second time we put the money in, we get two, or vice versa. So either way, we're getting three pops. It was a huge win. Now, I would say that machine does not represent a function. Even though we got the right flavor, it was black cherry for what it's worth. It's not a function, because every time you press that button, you should get one and exactly one output. You should get exactly one pop in this case. You should know exactly what you're going to get. Now, this machine, it was broken. Essentially, there was an error. There's something wrong with it. It benefited us, but it still wouldn't represent a function, because every time you press the button, you should get the exact same result. Okay, let's define a few words. The first word I want to define is relation. So a relation is information that can be represented by a set of ordered pairs. Remember, an ordered pair looks something like this. Say like 1, 2, and they're in parentheses. You could graph this. We know that the first term is always the x value and the second term is always the y value. So in general, an ordered pair is something written like this, x, y. They can be positive, they can be negative. It just tells you where to go on the Cartesian plane. The x is how far you move left or right, and the y is how far you go up and down. Now, in the context of this vending machine and whatnot, what does this mean? Well, x and y are the input and output of any function, any sort of relation. So for our relation with the vending machine, if I press that purple Gatorade button, the input, or the x value, is me pressing the purple Gatorade button. The output is whatever the machine does in response. Now, if it's a function, it's going to give me purple Gatorade every time. If it's not a function, it might not. Something might go wrong, or it might give me something else, or it might double up on my cans of purple Gatorade or bottles or whatever it is, like the one I just told you about at the grocery store. But a function is something you're going to get the same thing every single time. A relation is just some sort of relationship with an input and output, and you're not necessarily sure what you're going to get every single time. Okay, I spoke to this a moment ago, but a function is a relation. It's a special type of relation. So not all relations are functions, but every function is a relation. So a function is a relation where each input has exactly one possible output. Again, vending machine, purple Gatorade button. The only possible output for a functional vending machine is one that gives me the purple Gatorade when I press the button. Okay, now functions are normally represented in one of 4 different ways, and I'm going to talk through each one of those here in just a moment. One of the possible ways that we would represent functions is by using ordered pairs. So we talked about this a moment ago. An ordered pair has an x component and a y component. This is a function. I just made it up. There's no special meaning to this particular function, but this one is indeed a function, and let's examine why. So here, if we plug in 1 to this function, there's only 3 points to this function, 3 inputs, 3 outputs. So if we plug in 1, we know that 7 is going to be the output. Now in the same way, if we plug in 2, 10 is going to be the output, and if we plug in 3, 13 is going to be the output. So if this was a vending machine, there would be 3 different buttons on it. 1 is 1, 1 is 2, 1 is 3. So we know what's going to happen with each of these particular inputs. The second way you're going to see functions represented is by the use of tables. I use the same function here that we did with the ordered pairs. Note that the x's are all just in a column and the y's are all in a column. So our inputs are on the left, outputs are on the right. If we plug in 1, we're going to get 7. Plug in 2, we're going to get 10. Plug in 3, going to get 13. The same logic, same everything really. It's the same exact function. It looks exactly the same. The only difference here is just how we chose to represent it. Here's our third representation. It's called a mapping diagram. We aren't going to see these as often, but it's good to be familiar with them. So what this is this is all the set of inputs, this X column here. Notice how it looks really similar to the table. And then this is all the set of outputs, these Y's here. Now what these arrows represent is if you plug in 1, 7 is going to be the output. If 2 is the input, 10 is the output. If 3 is the input, 13 is the output. Now, sometimes you'll see these and the arrows don't necessarily go straight across. You might be thinking, like, what's the point of this? It looks just like a table. That's a fair critique. Well, sometimes maybe there's more inputs than there are outputs or vice versa. And sometimes there'll be multiple, like if you plug in 1, they'll have multiple outputs. Or if you plug in maybe 7 as an output, it has multiple inputs. Now, of course, not all of those would be functions because we know that a function is a relation where each input has exactly one output. But sometimes you might see something where if you plug in 1, you get 7. If you plug in 2, you also get 7. This would be like looking at our vending machine a moment ago. And if you remember, it had 2 different buttons that had Pepsi in them. So actually, let's pull that up real quick. So notice here, there on the top left of those buttons there on the machine, there's 2 of them that say Pepsi. So both of those are 2 different inputs, but you're going to get the exact same output. Still a function because you know exactly what you're going to get with this one. Okay, the fourth way we're going to see functions represented is with graphs. Now, I just scribbled this one out. This isn't very pretty, but it is what it is. You can see here on the x-axis, we go from -3 to +3. And on the y-axis, we go from -15 all the way up to +15. Don't worry about the scales. It's not really that important. The important thing here is noticing these 3 points. Now, these 3 points are graphed at 1, 7, 2, 10, and 3, 13. That's the same information we used in the table, the same as in the ordered pair, same as in the mapping diagram. So all 4 of these are ways that we can represent the same exact function, the same exact data. Okay, let's wrap this thing up. So here's the key takeaways. First one here, X is always the input. Always, 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 always. X is always the input. Y is always the output. If you're like me, I have a hard time remembering which one is which. So the way I think of it is X comes before Y in the output, or sorry, X comes before Y in the alphabet. So X must come first. The input is always going to come before the output. So the output depends on the input. Again, this is me pressing the button, and this is me receiving my beverage. Okay, and function, this is the key takeaway here. Each input has exactly one possible output. You know exactly what you're going to get. Think of a vending machine when you think functions. A vending machine that works. A vending machine that works represents a function. Okay, let me know if you have questions. You got this.